Hello all, I want to welcome you once again to our class. Today we will be talking about reaction rates and mechanisms, reaction mechanisms. We're going to know what these terms mean as we move on. But before we do that, as usual, I have something for you this time. I don't have a quote, I have a meme. Gram is measured in grams G, milligram in mg, kilogram in mg. What about Instagram? So Instagram will be measured in what? Will be measured in IG. That is what it means. And that is just what it means to relax at this period. Alright, so let's take it off from there. Our learning objective today will be to understand rates, reaction rates, and factors affecting it. Secondly, we're going to know how to draw and interpret energy diagrams of chemical reactions. Those are the two things we intend to achieve at the end of this class. So let's take it off from there and begin to get into it. Spontaneous and non-spontaneous reaction. A spontaneous reaction is a reaction that takes place naturally on its own without having to be prompted, without having to be caused by anything. There is no stimulus to it. A good example is when you drop a ball on the mountain. If you just drop this ball will keep flowing down because it is going down a gradient. And this is a spontaneous process. You do not have to push it, you do not have to do anything to it. This ball is going to roll down. Such processes are what we call spontaneous process, and that will be akin to what we're going to explain today. Some chemical reactions proceed on their own without having to be stimulated by any force or addition of any energy. They just occur naturally on their own. On the other hand, there are reactions that cannot take place on their own, except they are being stimulated or someone forces them to take place. You have to prompt them in one way or the other. Such a reaction is what we call a non-spontaneous one. A non-spontaneous one is like if you're asked to move a block up a mountain, even if that block doesn't weigh a lot, you're still going to spend some energy to climb this mountain. So what it means is that you're going to add a form of energy. You need energy to complete this process. You need energy for this process. That is what this means. Okay, so having said that, let us take it to the next one. Entropy. Entropy measures the degree of disorderliness of a system. Some systems are better off suited when they are disorganized or random. In fact, when systems are much more disordered, its entropy is higher and reactions tend to occur in such a condition. What is that feasible? Reactions involve reactants. Remember, reactant, let's say reactant A must have to react with reactant B to form, let's say, a product. What this simply means is that the two of them need to keep colliding with each other. That collision is most at times not a friendly process. Most often than not, the collision is a vigorous process. So that if it doesn't get that vigorous, if it doesn't get that disordered, we're not going to get the product C. And you know, the end product of any chemical reaction is to form the product. So entropy is low when the organization is high. You know, if you look at it, there is high organization. Whenever there is high organization, entropy is actually low. But when there is high level of disorganization, look at it, there is disorder. Here, the entropy is high. So entropy measures the disorderliness of a system. And in thermodynamics, reactions favor any reaction that will take place spontaneously will have a very high entropy. Reaction rate. What does reaction rate actually mean? You know, this is forming bulk of what we're going to be talking about in this particular lecture. Now, reaction rate simply measures the speed of a reaction. How fast does a reaction take place? That is exactly what the reaction rate is. You see, some reactions, naturally, like we said earlier, some reactions proceed faster than the others. While some of them occur very fast, some of them occur very low. You see, some reactions in nature proceed faster than others and can be manipulated in either way, either to make it fast or low, depending on what you want. If you want to get more of the product, what do you need to do? You need to manipulate in such a way that the reactants will collide more vigorously to form the product. Now, experimentally, it is determined by estimating the rate of disappearance of the reactant or the rate of formation of the product. Now, let me give you a good example. You remember, if we have A is going to B, if A is my reactant and B is my product. Now, what is happening here is that A is reacting, means it's going to disappear to form B. So the two things I can do here now is that the concentration of A decreases with time. As time passes, it decreases. The concentration of B increases with time. Now, if I use the knowledge of increase and decrease, I can only say that A is disappearing. As it disappears, it forms B. So if I can measure the rate of disappearance of A, which is a change, that means A is going to change with time. I can also measure the change of the product with time. In fact, A here now, the square bracket, remember we used it last time? Square bracket here of A simply means concentration of A measured in molar. Concentration of A usually is a molar concentration. This means concentration of B, again it is measured in molar, and then delta T simply means change in time. This means change. Just change, and T is time. Let me put it here, and T simply means time, because as time passes, this takes place. So if you, at any point in time, you can measure the rate of disappearance of the reactant or the rate of formation of this, we're going to determine R, which represents the rate of this chemical reaction actually occurring. So a reaction mechanism simply is a detailed explanation of how a chemical reaction takes place. Now, there are important underlying assumptions that are highlighted here. We're going to talk about it. Number one, you see, reactant particles must collide. Reactant particles must go into fight for a reaction to occur. Now, like I said, most times the collision between the reactant particles is not a friendly collision. The collision is in such a way that you want to form reactant, you want to form product, and as a result, there has to be this vigorous collision for this to take place. So if they don't collide, if they just get in there and sit on one another and begin to look at each other without having to get into this fixed fight, no reaction takes place. Number two, the particles must collide with at least a minimum total energy. Yes, they have to collide with a minimum total energy. Now, this minimum total energy is what we call activation energy, which I'm going to introduce in the next page. It's called activation energy. Let me just write it in full. Activation energy. So now, it's not just enough for them to collide, but this collision has to be effective in such a way that they achieve what? That energy. And colliding reactants must be oriented in such a way that they can fit into each other. What I usually tell students, that reactants fit as what we call the lock and the key. Remember, if you put your lock into your key, they're going to fit into well. So I usually tell students, I usually give them this good example. Now, if I have a T-shaped reactant to be A, and I have U-shaped, kind of square U, to be, this is A, this is B, and they get into this, they have to fit into each other for this reaction to take place. So what it means is that they're going to fit perfectly into each other this way for them to form the product. That means this orientation must be perfect. If these three factors are not met, the product of the reactions cannot be formed. So what is then this activation energy I just talked about? Activation energy simply means the energy barrier that the reactants have to cross for them to form the product. In other words, it is the minimum. Actually, it is a minimum amount of energy. It's a minimum amount of energy required by reactants so that a chemical reaction will proceed. And what happens there is that at the level of activation energy, bonds of the reactant molecules are broken to form the new bonds for the product. So you can just say it is the kilomanjaro of the reactant. The reactants have this challenge of overcoming that mountain. Now, if I have an energy diagram like this, and if I draw it this way, okay, I'm going to make it a little bit beautiful. It's a freehand sketch. Now, this is the energy of the reactant. Let me just say reactant energy. Energy. This is the product energy. Now, this is usually plotted energy versus reaction progress. This is energy versus the reaction progress. That is how this graph is plotted. Now, if you look at this now, these are the reactants. The reactants have a hurdle to overcome. What is that hurdle? The hurdle they need to overcome is for them to climb this mountain. This mountain they need to climb is what we call the activation energy. And if they don't climb this mountain, no product is going to form. The shortcut we call it EA. And in fact, at the top of this peak, at the top of this mountain is what we call the transition state. That's what we call the transition state energy. So every reactant has to climb this mountain, get to this transition state, which is the highest energy of this activation, so that the product has to be formed. At this transition state, like I said again, the bonds in the reactants are broken so that the new ones for the product are formed. And that is exactly what happens there. So that will take us to what we call the energy diagrams. Energy diagrams is just a plot of energy versus reaction progress. You can see energy versus reaction progress, energy versus reaction progress. In this reaction, it shows you important things we're going to be talking about. Let's try to label it. Number one, we'll start with what is here. At this point, you have the energy. Remember, every reaction has to start with what? Energy of reactant. So you have the energy of the reactant to the left. So here we have what? The energy of the product to the right. Now, what else do we have? Remember what I told you? I told you already that at the top, at the peak of this mountain, remember I said, the peak of that mountain, something is happening there. At the peak of this mountain, we say this is called, the peak is called the transition state. Or, if you don't call it the transition state, you don't know that well. The transition state, that's not as good as I wanted, yeah. Or, you can say it is the activated complex on top of that mountain. That is what you call it. Then, again, we can now put other stuff. Now, if you look at this, the energy of the reactant and energy of the product, we can trace this thing down. Now, if you start from, let's say, 0, what it means, this will go up. So let's say this might be 100, and this is also increase in reaction progress from, let's say, 0 to some other time at a particular time there. Now, if you do this and do this, you're going to observe something. You're going to observe that the reactants here need to overcome this energy. This energy here, remember again, what do we call it? Is the energy they need to climb for them to form the product. And this energy is what we call what? This energy is what we call activation energy. Again, remember, activation energy. It is EA. And then, we're not done yet. Now, if you look at this, now the energy of the product, energy of the reactant and product is not the same. If you look at this, the energy of the product is less than the energy of the reactant. So let's put this. Energy of the product is less than the energy of the reactant. in this type of reaction, that's what we call it exothermic reaction. And in exothermic reaction, the energy of the reaction is a negative. So the difference between the energy of the product and the reactant is what we call this. And I'm going to use a different color. So if I label this now, I'm going to call this what? Energy of reaction or heat of reaction. And this energy of reaction is negative for exothermic reaction. And the reason why that happens is because you are doing product minus reactant. And when the product is less than what you are subtracting from, that becomes what? A negative sign. This is what we call the exothermic energy diagram for exothermic energy diagram. Now let's go to the endothermic. In endothermic reaction, it is the opposite of what is happening here. How opposite? Direct opposite. If you look at this, let me start with those ones first. Now, here is the energy, of course, of product. That's what we have here. The energy of the product. Again, here we have, just here now, we have energy of the reactant. If you look at it again, the energy of, look at it, let's put it this way. You see, the energy of the product is now greater than the energy of the reactant. Therefore, we have a new change in energy. When you do the change in all of them, in this case now, the energy of the product is greater than the energy of the reactant. And then, if you do it, you say, okay, here is a negative sign. Wait, I didn't put it. It's going to give you a positive sign. So here, you see this now, let me label that one first because that's the main difference. So this is what we call the energy of the reaction. Energy of reaction. And the energy of the reaction at this point is a positive sign. And the reason why that happens is because the energy of the product is greater than the energy of the reactant. And then let's finish other labeling there. Other labeling there will be, now let's label the peak of this mountain. Remember, the peak of this mountain remains the same thing. This is what we call the transition state. You're expected to know this and reproduce it in exam. Or activated complex. Yes. And then we're not done. Let's now label the. Now you see, look at this now. The difference between now the reactants have to clamp compared to this one. The reactants have to clamp a higher energy to form the product. In fact, I'm going to use a different color. If I use a different color in this case, you see that it is a whole bigger than what we had here. And this is actually the activation energy of this. The activation energy of this reaction. So this is how we label. These are all the components of both the exothermic and the endothermic reaction and the main difference between the two. Factors affecting rate of reaction. There are 4 factors affecting rate of reaction that we're going to look at. Number 1, the nature of the reactant, concentration of the reactant, temperature of the reactant, and the presence of catalyst or inhibitors. Let's take that one by one. Now, reactions involving ionic compound occur faster than those involving covalent compound. The main reason is because there is oppositely charged ions. Remember, if you have sodium chloride, what you have is these balls plus these guys. These guys quickly ionize in solution and get into reaction. Now, this type of reaction do not actually need a catalyst or something to force them because they're going to react naturally in their own. So, because the reason why is that these ions are strongly attracted to each other of opposite electrical charges. So, example of what you have in precipitation reaction, you find out that they swap the ions because they can easily attract each other and swap the ions, and the reaction will take place without having to be prompted. If you compare this with covalent compound, covalent compound reacts slowly, and part of the reason why they react slowly is because these covalent bonds are a little bit strong. And what happens first is that those bonds need to be broken first so that they can achieve the activation energy. And by the time they break that bond and they begin to form a new ones, that takes a little bit of time. That's why covalent compounds react more slowly, or you can say slower, than ionic compound. And then the last thing we're going to consider as the nature of compound is that the physical state. Remember, gases are the most energetic state of matter, most energetic, because they're always moving about. They have high kinetic energy. The solid are the least. So gas molecules tend to, and the reason why they do this is because of the molecular size and the bond polarity. Then the size is small, they have higher surface, and they can easily go into reaction without anything. So the bond size too matters. The shorter the bond, the easier the reaction begins to react, and then the bond polarity. Molecules that are much more polar will tend to get involved in a chemical reaction. Molecules with a polar bond, because polar bonds are much more stronger than molecules that have only non-polar bond. And we need to understand this relationship with the intermolecular forces. Let's go to the next stuff. Now, we talked about collision. We've been talking about collision all this while. Now, what type of collision is needed for a chemical reaction to occur? Now, a collision that causes a chemical reaction to occur between the molecules must be effective. That collision is said to be effective. So if the collision is not effective, it doesn't make any sense, the reaction is not going to occur. And for a collision to be effective, what happens? Now, number one, there must be reactants must have the collision is effective when it happens between, number one, the reactant for a desired chemical reaction. You must have the necessary reactants that are needed for that chemical reaction to occur. Number two, they must have the right amount of energy. Which energy? They must have the proper activation energy for that reaction to occur. And finally, they must be properly oriented, like I showed you already. If the orientation is not there, so you find out that effective collision have all these pieces. For it to work well, it must have to be with the desired reactant for the chemical reaction. It must be with the proper amount of energy, and those reactants must have to be in a good orientation for them to fit into each other, and reaction will take place. Concentration of reactant. Now, concentration is like overcrowding. Of course, the higher the concentration of reactant, the higher the concentration of reactant, the faster the reaction. Then the reason why this happens is because, what's the reason? The reason is because there is more collision. And the more the collision, the more the possibility of being effective collision, and the more the reaction. So more collision will also lead to increase in chemical reaction. Because they are so crowded, they begin to hit each other and impact those collisions, and the higher these collisions, the more the rate. So that's why I said there is more likelihood of collisions when reactants are very crowded in the containing vessel. Now we go to the next factor. The next factor here, temperature. You see, temperature is also something related to collision, because you see, increase in temperature will increase kinetic energy. And kinetic energy simply increases the speed. Remember, speed. Let me call it V, speed of molecules. And if the speed of molecules increases, it will result what? Let me put it rather well. Results to more effective collisions. And more effective collision simply means faster reaction. That's exactly what it means. So that's exactly what happens here. So the increase in temperature of a system increases the average kinetic energy and the internal energy of the reacting molecules. So increase in this velocity will increase the number of molecular collisions. It will increase the number of molecular collisions that take place in a fixed amount of time, and hence increases the rate of a reaction. So the greater kinetic and internal energies of colliding molecules will enable larger fractions of those collisions, and they will provide the necessary activation energy for reaction to proceed. Now the next thing, catalysts. We're getting close to the end of this class. You see, what does catalysts do? Catalysts are substances that speed up the rate of chemical reactions. That's the language we say. They speeds up the rate of chemical reaction. What do? They simply do that by cutting the activation energy and providing an alternative pathway for the reaction to proceed faster. What do they do? Now remember that I'm going to use a different color. Now remember, I'm going to show you in each of these drawing, I'm going to show you the catalyzed and uncatalyzed activation energy. So I'm not going to label every other thing there. Now, if you look at this now, this is a normal activation energy. Call it normal or uncatalyzed. Let me say normal, or you can say uncatalyzed. Uncatalyzed EA, activation energy. Now, when a catalyst gets involved, what happens? It's going to cut this thing to a particular number. Let's say it becomes this. No, that looks too crowded. I'm going to make it cleaner. So, no, it's still not good to me. Okay, good. Now, maybe I'm going to remove all I have there and then make it better. Okay, so I'm going to have something like this. Make it a little bit bigger to be easier for me. Okay, now I'm going to use a blue to put the new activation energy. You see, this becomes activation energy. You can say catalyzed activation energy. You see, it cuts down, what it actually does is to cut down the amount, that barrier, that energy barrier. Remember, this energy barrier has the, I told you, the peak of this energy barrier is the activated complex. So it provides a new peak so that this reaction doesn't have to jump this high, but it can jump a little bit and then they begin to form the product. This is what the catalyst do. This is the mechanism of action of a catalyst. Now the same thing happens here. This is extra. In endothermic reaction, of course, in endothermic reaction, you usually have a longer activation energy. That's why most reactions here are not spontaneous. So if you look at this, this is a normal one. In a normal one, look at how high it is. What does it do? It comes there, it cuts it down to something this way. So if you look, if you now draw a new activation energy, it's going to be from this peak to here. And this becomes, remember, this is the normal, this is the catalyzed EA, and the one we have here is the uncatalyzed EA. Remember again, EA means, remember that EA is activation energy. I used this earlier in this chapter. So this is the mechanism of action of catalyst or even enzymes. In fact, enzymes are just said to be what? Organic catalyst. Organic, remember, enzymes are organic catalysts. That is exactly what they also do, because they are encountered in living organisms. They facilitate those reactions in the living thing. Now, the last but not the least of what we're going to be talking about here today will be the inhibitors. What do they do? That is the last page we're going to be talking about today. The inhibitors are substances that do what? They decrease the rate, the reaction rate. That's exactly what they do. The inhibitors decrease the reaction rate. And the way they do it is that they do the exact opposite of what the exact opposite of what the catalysts do, by doing what? Increase the activation energy. Now, they increase the activation energy and increase the peak of the mountain that the reactants have to climb, and the reactants cannot climb it. And even at times when they climb it, they don't produce a lot of the product. That's exactly what they do. So what will they do? Now, you see, if you look at this now, again, this is the normal activation energy. What this thing does is to increase this, and then you find out that we're going to have a different activation energy that is larger than the old one. And in this process, it does what? It increases, or rather, it decreases the rate of chemical reaction. So if you look at the normal activation energy here too, is this one. Now it comes and does its damage by increasing this, and this process is what actually, so you can say this is inhibited EA. This is the inhibited activation energy. So what they do is that these guys, the inhibitors, do the opposite of what the catalyst and enzyme does. In fact, many poisons that have been developed, many poisons and some medicines inhibit one or two enzymes and decrease the rate of those reactions. That is how most of these enzymes have been designed, so that some of those pathogens that host themselves in the body and cause problems, they produce enzymes and proteins. So what the body does is to inhibit those. What the drugs do is to inhibit one of those two enzymes that help them to survive, and in such a way they are poisoned and they die, and a human being recovers from the sickness. Now, some substances normally also found in the living things inhibit specific enzyme catalyzed reactions in the body. Now, this is not only applied in medicine in this way, but some natural reactions that take place in the human body, enzyme catalyzed reactions, are regulated in this means. A good example is the feedback inhibition, whereby a specific product, now if this is, let's say, product A produces B, B produces C, C produces D, and D produces E. Now, an enzyme is facilitating this reaction. What happens is that when there is too much of, an enzyme, let's say ENZ, when there is too much of E in the body, what does it do? This E will come and tell this enzyme, okay, stop action. So it will be a source of inhibition for this enzyme, so that it will stop making this product that will lead to the making of the E, because it is in excess. This type of inhibition is a reasonable inhibition that happens in biochemical and metabolic process, and this is called a very beautiful name. We call it the feedback inhibition, and this is made possible because of the feedback process that allows metabolic intermediate not to be concentrated too much in a particular host cell. All right, at this juncture, thank you for listening. I will see you in another class. Have a wonderful day.